So, now we are going to solve the same second order ordinary differential equation for negative lambda values. So, we set lambda equals to negative a squared, then my ordinary differential equation becomes x double dot minus a squared x equals to 0. Now, to solve a second order differential equation with constant coefficients, what we do is we get the characteristic equation. For this particular problem, the characteristic equation is r squared minus a squared equals to 0. This means r equals to plus or minus a. Then we can get the solution x of x, and it equals to, so let us say a2 times e to the ax plus b2 times e to the negative ax. Or sometimes some authors write the same solution using hyperbolic trig functions. So, or let us say a2 tilde hyperbolic cosine of ax plus b2 tilde times hyperbolic sine of ax. Again, these two solutions are equivalent, and these are two ways to express the same solution. Okay. So, if for negative lambda values we have x of x equals to this. So, we finished two cases. The next step is to consider positive values for lambda. Okay. So, that is case 3, let us say C3. So, now lambda is positive. So, let us say lambda equals to a squared. Okay. If lambda equals to a squared, this differential equation becomes x double dot plus a squared x equals to 0. The characteristic equation is r squared plus a squared equals to 0. This means r equals to plus or minus I times a. This I is the complex imaginary number. Now, in this case, our solution x of s equals to, okay, so I used a to b to, let us say a3 cosine ax plus b3 sine ax. Okay. Okay, now let us see. So, this was our original second order ordinary differential equation with constant coefficients. Since we do not know the value of lambda, we consider all the possible cases for lambda. In fact, lambda can be 0, lambda can be a negative number, or lambda can be a positive number. If lambda equals 0, then we obtain the solution for big X of x, which is a1 x plus b1. For negative lambda values, x of x equals to this one, a2 e to the ax plus b2 e to the negative ax. Now, for positive lambda values, the solution for big X of x equals to this this one, a3 cosine ax plus b3 sine ax. So, the next step is to figure out the values for these constants using the boundary conditions. Okay, now, let us recall the boundary condition. The one boundary condition says the u at the left end point equals to 0, and the second boundary condition says u at, I think it was x equals pi, and this temperature value is 0 as well. Okay, now, using these two boundary conditions, let us figure out the boundary conditions for our big X of x. Okay. So we know that u of x comma t equals to big X of x times big T of t. Now if you evaluate this one at x equals 0, we have big X at 0 times T of t, and my first boundary condition says this one equals to 0 for all t. So in other words, so this is does not equal to 0 because we consider all the possible t values. Then the only possibility is big X of 0 equals to 0. In the same way, we can get the boundary condition of big X at pi, and you should get 0 as well. Okay, great. Okay, now let's consider. Okay, so we have this is a one possibility. Let's say equation 1. This is another candidate for our big X of x, and we have a third candidate which is this. Let's consider the first equation. Big X of x equals to a1 x plus b1, and big X of x should satisfy these two boundary conditions. So if you evaluate big X at 0, then you have a1 times 0 plus b1, and this one must be 0. So this says b1 must be 0. Let's use the second boundary condition, x at pi equals to, now we know that b1 equals to 0, therefore we have only a1 x term. So a1 times pi, and this one equals to 0. From this we get a1 equals to 0 as well. So this means if our big X of x equals to a1 x plus b1, and if it satisfies these two boundary conditions, then big X of x should be equal to 0. So this is the trivial solution. Okay, now let's see whether we can get any information for a2 and b2 using the same boundary conditions, and I will do in the next video.